Welcome to the last video of our series on trig substitution. In this video, we'll look at the last case where our integral involves the square root of x squared minus a squared. But as a quick recap, remember for our first case, we looked at integrals involving a squared minus x squared. To solve these types of integrals, we made the substitution x equals a times sine theta. In our second case, we looked at integrals involving square root of a squared plus x squared. For these problems, we want to make the substitution x equals a times tangent of theta. For our last case, we'll be looking at integrals that involve square root of x squared minus a squared. For these problems, what we're going to do is make the substitution x equals a times secant of theta. Remember that in each of our previous cases, we made use of a trig identity to help us deal with the square root. In our first case, we used the trig identity cosine squared theta plus sine squared theta equals 1. In our second case, we used the identity 1 plus tangent squared of theta equals secant squared of theta. In our third case here, what we're going to use is secant squared of theta minus 1 equals tangent squared of theta. Let's work through an example together. Let's consider the integral of square root of x squared minus 16 divided by x squared dx. I can rewrite this as the integral of square root of x squared minus 4 squared divided by x squared dx. So, since we see a square root of x squared minus some number squared, we're going to make the substitution x equals, in this case, 4 times the secant of theta. Taking the derivative of both sides, we get that dx is equal to 4 secant theta tangent theta d theta. So now let's make our substitution. We have the integral of the square root of 4 secant theta squared minus 4 squared divided by 4 secant theta squared, and then the dx gets replaced with 4 secant theta tangent theta d theta. Let's now try to simplify what's under the square root. We have the integral of square root of 16 times secant squared of theta minus 1 divided by 16 secant squared of theta times 4 secant theta tangent theta d theta. Using our trig identity, I can replace the secant squared theta minus 1 with tangent squared theta. So this gives us integral of square root of 16 tangent squared theta divided by 16. I have a secant squared theta in the denominator and a secant in the numerator, so these will cancel out, leaving me with just 1 secant theta in our denominator. And then I have 4 tan theta d theta. As we've seen in our previous examples, what's under the square root here is a perfect square. So this reduces to the integral of 4 tangent of theta divided by 16 secant of theta times 4 tangent of theta d theta. So in the end, our integral looks like the integral of tangent squared of theta divided by secant of theta d theta. Looking at this integral, it's not immediately obvious how I would find the antiderivative. But what I can do is try using our trig identity again. I'm going to replace this tangent squared theta with secant squared theta minus 1. My hope is that since there's secants there, some things might cancel out and I might end up with something that's a little bit simpler. So when we make that substitution, we end up with the integral of secant squared theta minus 1 divided by secant of theta d theta. Now splitting this fraction up, we end up with the integral of secant theta minus 1 over secant theta d theta. Now this integral looks a little bit more manageable. we have integral of secant theta, and we can think of 1 over secant theta as just cosine theta. So this is secant theta minus cosine theta d theta. And each of these individual terms I know how to integrate. In our previous video, we learned how to integrate secant theta. We found that the antiderivative was ln of absolute value of secant theta plus tangent theta, and then the integral of cosine of theta is sine of theta. So I have minus sine of theta and then plus c. Now all we have to do is rewrite this back in terms of x. In the beginning, we made the substitution. X is equal to 4 secant theta. So now we just have to solve for theta. Divide both sides by 4, I get x over 4 is equal to secant theta. So theta is equal to arcsecant of x over 4. So plugging that in everywhere I see theta, we get ln of absolute value of secant of arcsecant of x over 4 plus tangent of arcsecant of x over 4. Then we have minus sine of arcsecant of x over 4 and then plus c. If we look at our expression here, we see arcsecant of x over 4 inside various trig functions. We have secant, tangent, and sine. So what we're going to do is imagine a triangle where one of the angles is arcsecant of x over 4. Remember that a secant of an angle inside a right triangle is the hypotenuse divided by the adjacent side. So let me draw a right triangle where the hypotenuse is x and the adjacent side is 4. Then the arcsecant of x over 4 would be referring to this angle right here. Now, if I have a right triangle with side 4 and hypotenuse x, using the Pythagorean theorem, we can find that the remaining side has length 16 minus x squared. So if I want the tangent of that angle, I would do opposite over adjacent, which would give me the square root of 16 minus x squared divided by 4. And if I want the sine of that angle, I would do opposite over hypotenuse, which would be square root of 16 minus x squared divided by x. So my antiderivative is ln of absolute value. The secant and arcsecant cancel out, leaving me with just x over 4. The tangent of arcsecant of x over 4, again, that's opposite over adjacent, which means I have square root of 16 minus x squared divided by 4, minus the sine of the secant of x over 4. That's opposite over hypotenuse, which is square root of 16 minus x squared divided by x, and then plus c. So that's my final answer here. So that's it for our series on trig substitution. Thank you so much for watching.